Okay, this video is about hypothesis testing for proportions. And proportions, as we've already seen, always end up with a z distribution, so that's nice. Among the key facts to remember, the data is categorical, and we are keeping it simple so there are only two possible outcomes, like a yes or no question. And here is the formula for z when we are dealing with proportions. Remember that p hat is the sample proportion and p is the parameter representing the population proportion. Let's try our first question. We are testing left-handedness and we are testing to see if the proportion is less than 1 in 5 or 20%. So we are going to assume that p is equal to 0.2 as our null hypothesis. And we are only going to reject if the sample proportion is too small. So this is a one-tailed, left-tailed hypothesis. Here is what the distribution looks like, assuming that the population proportion is 0.2. This question is asking about the 1% critical value for the test. So there is a number k such that if the sample proportion is below this number, then we would reject the null hypothesis. We know that if there is 1% area in the left tail, then z is equal to negative 2.326. Set this equal to the formula for z and plug in the information from the question. Note that the null hypothesis assumes that p is equal to 0.2, and we plug that in for all the p's in the formula. Solve for k, and we get 0.1342. So if the sample proportion were less than 13.4%, then we would reject the null hypothesis. Since the sample size is 200, that would only happen if 26 or less people were left-handed. New question. This time we are testing the proportion of students who go out drinking. We are testing that this proportion is greater than 60%, so we will assume that p is equal to 0.6 as the null hypothesis. And we will only reject if the sample proportion is too large. So this is a one-tailed, right-tailed hypothesis. Here is what the distribution looks like, assuming that p is equal to 0.6. Our sample proportion p hat is 48 out of 75, or 0.64. The p-value is the probability of getting a result as or more extreme than this, so that is the area in the right tail beyond 0.64. To find this probability, you create z by subtracting by p and dividing by the SD. Note that p is equal to 0.6 under the null hypothesis, and it shows up in the SD2. So z is greater than 0.71, and if you check the z table, you'll see that this probability is 0.2389. This is a fairly large p-value, and it is not going to be a rejection. We do not have enough evidence to conclude that more than 60% of students go out drinking. Okay, we have the same question and hypothesis from before. This time we have an unknown sample size. P hat is equal to 0.62, and the p-value is 0.0985. Here is the distribution once again. P-value is the probability of getting a result as or more extreme than the sample proportion. So the p-value is the area in the right tail beyond 0.62. Looking at the z table, if the area in the right tail is 0.0985, then z must be equal to 1.29. So I'm going to set the formula for z equal to 1.29 and solve for n. You should get an answer of 999 students. Always round up when doing sample size calculations. Okay, we learned earlier in the term that if you roll 2 fair dice, then the probability that they add up to 7 is 1 out of 6. Since we are going to assume that the dice are fair, our null hypothesis is that this probability is 1 out of 6. This is a two-tailed hypothesis, so I'll reject if the sample proportion is too large or too small. Either way, that would mean that the dice are unfair. So I rolled 2 dice 300 times and got a sum of 7 only 36 times. So my sample proportion p hat is 3 over 25. Here is what the distribution looks like under the assumption that p is equal to 1 over 6. Let's put the sample proportion into the picture. P-value is the probability of getting a result as or more extreme than 3 over 25. Since this is a two-tailed hypothesis, extreme could be defined as above or below the mean, and the area contained in both tails is the p-value. You can verify that 16 over 75 is an equal distance above the center of the distribution, but it's not actually important since I'm going to use symmetry. I'm just going to find the area in the left tail and multiply it by 2 to find the p-value. Create z by subtracting p and dividing by the SD. Remember that p is assumed to be 1 over 6 in the null hypothesis. We get z less than negative 2.17. And looking in the z table, we see that the area in one tail is 1.5%. So the p-value is 3%. This p-value is pretty small. I didn't specify the level of the test in the question in the previous slide, but regardless, this small p-value makes me very suspicious that the dice are unfair. Okay, this question is once again about Shaq's free throws. Much like in the previous video, I'm given a confidence interval and I want to know what I can say about this hypothesis test. We have a two-tailed hypothesis, so the first condition is met, and I'm going to check to see if the null hypothesis is within the confidence interval. 2/3 is not inside the interval, so we would reject the null hypothesis at 5% level. It has to be 5% level since the confidence level was 95%. Furthermore, it proves that Shaq makes less than 2/3 of his free throws because this entire interval lies below the null hypothesis. Okay, now you have 3 questions to do on your own. Good luck with that, and I'll see you in class.